Hi everyone, this particular lecture is called Multiple Regression. Now we covered simple linear regression where in developing the relationship with the dependent variable there's only a single independent variable. So when we have one independent variable we refer to that as simple linear regression. When we have multiple independent variables we refer to that as multiple linear regression. So an example of that would be, what if we were testing a relationship between the selling price of a used car and the amount of mileage on it and its age? Because sometimes some people put a lot of miles on a car in a very short period of time versus a few miles in a long period of time, or there is some kind of like general standard. I know for Nova Scotia we often think that it should be somewhere around 20,000 kilometers per year. So is there a relationship between those two variables, the mileage and the age and the price of the car? That's the sort of selling price of a used car. And I'm sure that definitely there is, because I do look at myself, I do look at the age and I do look at the mileage on the car and somehow feel that the price should reflect those two things. All right? So we want to get into multiple regression because it's also quite common to use that approach in forecasting. Whenever we're doing either product forecasting, service forecasting, forecasting in general, the item that we're trying to forecast or the variable that we're trying to forecast is often related to more than one variable. Now, granted, at this point in time, we're going to just study linear relationships, but it is also possible that you could have nonlinear relationships as well, in which case we could get into nonlinear regression, logistic regression, or somehow curvilinear regression and so forth, all right? We could get into that. So I'm going to go through a couple of PowerPoint slides and then I will do a quick demonstration in Excel and how we use this. We're not going to do a bunch of computation by hand with multiple linear regression because the formulas can be a bit unwieldy. So we're going to stick with spreadsheet software, Excel in that case, to do that for us. If you have SPSS, Minitab, Stata, whatever else you got, SAS, you certainly can do a regression in those using those software packages as well. So essentially a regression line, the population regression line looks like this. Y is equal to beta 0 plus beta 1 x1, beta 2 x2, etc. if we have p independent variables. And then we have plus epsilon, because epsilon is necessary because it's not a perfect relationship. So we have to, do an error term that we would have to probably do some adjustment on the value that we get from the equation itself. So beta 0, beta 1, beta 2, etc., those are coefficients of the regression model, and those are the population parameters. Beta 0 is the intercept, and then of course the beta 1, beta 2, beta 3, and so on represents the coefficients of the independent variables, the respective independent variables. With simple linear regression, we would have stopped at beta 1 x1. But with multiple regression, we could go beyond one independent variable. The long run expected value of y, right, is equal to beta 0 plus beta 1 plus beta 2, etc., plus beta px. We drop the error term, and that is because the expected value of the error term is 0. In other words, the mean of the errors that we get from regression, if we were to plot all the possible values, that mean is 0. We could have put this, we could have said that this is plus expected value of epsilon, but the expected value of epsilon is 0. So if it is 0, we could just drop this term out of the equation. There's no need to keep it in there, all right? Yeah, because the errors are supposed to be randomly distributed about the mean of 0. So when we take a sample data and we fit an estimate to it, a regression estimate to the data, then we would get sample parameters. So B0 would be the sample estimate of the intercept, B1 would be the sample estimate of beta 1, and so forth. So as we can see here, those statistics are estimates of those population parameters. All right. And we interpret them in much the same way that we interpret the coefficients in simple linear regression. So this is the estimation process. We have a population equation that we were trying to estimate. We collect sample data, then we estimate the equation by using some software to assist us. We get the coefficients from that, and then those coefficients are our best estimates of the population parameters. The methodology that we use in fitting the regression line is a least squares method. And you may recall that we define an error as y minus y hat. This is an error, right? Let's call it E naught epsilon population. EI is yi minus y hat I. So if I sum both sides and I square it, then essentially I'm just taking the sum of the squared errors, which is equal to, right? So what we want to do is to minimize this, minimize SSE. Minimize the sum of the squared errors. So the regression line should make that a minimum for us. To calculate the coefficients that actually allow us to do that, we need to do some complex calculus. And so that's already done for us and inserted into our statistics software, so we don't have to do that ourselves. All right. Here's an example of a problem. I'm just going to show you. So we have this case here where a company is looking at whether or not there's a relationship between the salaries that it provides and the aptitude test score of applicants, or successful applicants, of course, and the years of experience that they have coming into the company. So we have two variables that could help predict the salary: the experience and the aptitude test score. So we could label one X1, the other one X2. So here's the population, of course, a regression equation that we want to estimate. Y is the annual salary, X1 is the years of experience, and X2 is the score on the program aptitude test. And we want to fit a regression equation to that. We take our input data, we plug that into our computer software, and then we get a least squares output. All right. And this is what the output could look like, where we have the coefficients. So that would be your B0, which is the constant, B1 experience, and B2. All right. That's the standard error, the standard deviation here of the coefficients. So for example, this would be SB0, SB1, SB2, right? Those are the t-values associated with each of the coefficients, and they allow us to be able to assess whether or not the coefficients are significant. So as you could see, but then of course we can't just tell from the t-value, we gotta look at the p-value. We could see that the coefficient of the intercept, which is basically B0, beta 0, is not significant based on this data. It's suggesting that the intercept is not significant. But this here, which will be the coefficient of experience, would be significant. And certainly the coefficient, the p-value associated with the test score also seems to be significant. All right? At a 1% level for sure, it definitely is significant. So that is the resulting equation. We simply take the statistics or the coefficients, and we now have, and we'll put a hat on top of that because that is an estimate of the true salary. This is the predicted value. The coefficients are interpreted in much the same way. BI represents an estimate of the change in the value of y, the value of y, right, correspond to 1 unit change in x. We know the intercept B0 is essentially just where the line cuts the y-axis. But then we interpret the coefficients of the independent variables in much the same way as we have done in the case of simple linear regression. In addition to getting the information on the coefficients and the test of significance, we could also do an analysis of variance as well. So we get an F table, and in that F table we will have the total sum of squares, the sum of squares due to regression, and then the sum of squares due to the error term. And we could get an ANOVA table that looks very similar to the one that we got in simple linear regression and interpret the values. All right. Excuse me. So this would actually be n minus 1. This is n minus p minus 1, where p represents the number of independent variables, and this is p. So we have two independent variables. So as you could see, then our degrees of freedom here, n minus 2 minus 1 is n minus 3, 17. Remember that n is equal to 20 programmers we're looking at in terms of the sample. So 20 minus 3 is 17. We have two independent variables, and n minus 1 is 19. So that's what we have here. We get our sum of squares, and then we get the MS value, just as we did when we were doing the F-test in ANOVA or the F-test in regression. Simple linear regression, that is. And then, of course, we know that this F statistic is the ratio of those two values. And we could then go and compute a p-value. The p-value would be the F value based on the 250.164 with 2 degrees numerator degrees of freedom and 17 degrees denominator degrees of freedom. In Excel, if you were looking at this, you would look for FDIS right tail. And you put in those parameters right here, your X value, your DF1, and your DF2, okay? That's what you would actually use if you wanted to get this value in Excel for you. We could also get a coefficient of determination, and the coefficient of determination is SSR over SST, 0.83 in this particular case, which is pretty strong. 83% of the total variation values of y can be explained by this regression equation. We're not going to focus on the adjusted multiple coefficient of determination. Some assumptions about the error term. Remember, I mentioned that the error term has a mean of 0, but then also an assumption about the error term is that it's normally distributed and that its mean is 0. So in which case we have a tendency to plot the residuals, the standardized residuals, and see if we have this sort of random pattern. If we have a random pattern distributed about the value of 0, then we say that the assumption that the errors are normally distributed is a reasonable assumption. Yeah? Test for significance of the regression is just the F-test. We get the results from the ANOVA table. And then the test of significance of the coefficients are the t-tests that we get from the summary of the coefficients. And I showed you that a bit earlier. All right? So if we're testing for the significance of the regression itself, we could put it as HO beta 1 is equal to beta 2 is equal to beta 3 is equal to 0. In other words, all of the coefficients are 0, so another way of actually writing that is that the regression equation is not a good fit. So we often refer to it as a goodness of fit test for regression, and then in this case the regression is a good fit. All right, the regression is a good fit, and so therefore, if we reject HO, the regression is a good fit. That means at least one of the coefficients is non-zero. And then, of course, we do that with the F-test of MSR over MSE, and then as long as we exceed our critical value, then we are able to draw the conclusion. In the case of the test of significance of the sort of coefficients, we will just look up the table. But just before I do that, this is just showing us what we've already gone through, which is the ANOVA output. All right, so I just don't want you to think that we're missing anything here. I've already done this. In terms of the test of significance of the coefficients, then of course you could see testing for any of the coefficients. Beta I is equal to 0 versus beta I is not equal to 0. And the test statistic is BI over the standard error. In the case of simple linear regression, we had it as T was equal to B1 because we only had one coefficient over SE divided by the square root of SSX. But that SE divided by the square root of SSX is really just SB1. SE divided by the square root SSX. That's just the standard error of the slope in that case, right? We are not going to do this calculation by hand. As I mentioned to you, the printout from the software will actually give us all of that information that we require. And so test for the significance of individual parameters, that's not correct. You never test for a sample statistic. You always test for a population parameter. So that should be beta I is equal to 0 versus beta I not equal to 0. And then we go back to the very same table that we have already looked at to show that those two are significant, but this one is not significant. All right? Which is the intercept. All right. Let's introduce this topic very quickly here. It's called multicollinearity. So when we have multiple variables, x bar 1, x bar, no, not x bar, sorry, x1, x2, x3, etc., xp, sometimes these variables can be correlated. There could be a correlation between them. If the correlation is too strong, then it is hard to be able to determine whether or not a variable acting on its own is having a major influence. We're not sure if it is because of the combined influence with a correlated variable that we're actually seeing the relationship between the dependent variable and the independent variable. So if R, the correlation coefficient between any two variables, is greater than 0.7, we are in danger zone, we are in dangerous territory, where it is possible that the effect that we're seeing could be from the combined effect and not necessarily from the individual effect of that independent variable. So it doesn't hurt that if we are about to do multiple regression, is to run a correlation on all of the independent variables to see if there are any pairs that are strongly correlated. And it is prudent to try to avoid using independent variables that are strongly correlated. All right? Now, in much the same way that we did estimation in simple linear regression, where we estimated the average value of y at a given x, and then we also try to estimate or predict the value of y at a given x, we could do exactly the same thing here, but except that instead of having a single value or a single independent variable, we have to do it with multiple variables. So we could be trying to estimate, do an interval estimation for the expected value of y when we have a given x1 and a given x2 and a given x3 and so on. Or we could try to predict a value of y for given x1, x2, x3, and so on. All right? I just want you to know that there is that similarity. However, the formulas that we would need to use are beyond the scope of our course. All right? Usually the software packages will give that to us. In terms of residual analysis, because we actually made the assumption that the errors are randomly distributed, around the mean of 0, then sometimes it's useful to plot the predicted values that we get versus the standardized errors. So you have to take each of the error terms and then divide it by the standard deviation of the error to convert it to a standardized error. Okay? And if we plot those, your standardized errors, we would call that standardized errors. We expect to see a sort of a no particular pattern around 0, right? As we plot the errors. Okay, and Excel will actually print off the errors and the standardized errors for you. Excuse me. So here's an example. We have these observations. Here's our predicted value of y hat, and here's the residuals or the errors, EI, and here are the standardized errors. And if we were to plot that versus this, we should not see any particular pattern. All right? Good. Something that looks like this, for example. Other than that, lastly, I want to just discuss the idea of categorical independent variables. Because sometimes when we're doing multiple regressions and so on, we tend to have categorical variables in the data. Particularly if in your survey you captured some demographic data like gender. So male and female, how would we capture that? In this case, you need to create what we call an indicator variable or dummy variable. So the indicator variable could say, okay, let's just call it G as the indicator, or gender, whatever we want to call it. Or instead of, well, first of all, that would be male, female, male, male, female, 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 etc. Then you could create a variable. Maybe you already have 2 variables in your data set, that is x1 and x2. So you could then call this one x3, and male could be 1, 0. Sorry, female could be 1, 0, 0, 1, 1, 1, and then you use those numerical values to actually do your predictions. All right. In the case where you have more than one level, so sorry, multiple levels of the categorical variable. So when it's only 2, it's binary, it's easy, 0 and 1. But if it's, say, for example, 3 levels, A, B, C. So if the number of levels, let's just call it K, you'll need K minus 1 dummy variables. All right. So ABC, I will need 2 dummy variables. I'll need let's call it x3 and an x4. And then you could say A could be 0, 0, B could be 0, 1, C could be 1, 0. You could decide that that's how you want to set it up. All right. And so, or you could make it B is equal to 1, 0, and then C is equal to 0, 1. It doesn't really matter. So as long as you're able to interpret what those actually mean. So you could do that so that you could actually run the regression equation and take into consideration the dummy variables, or the categorical variable. All right. So this is a simple case where we ask whether or not the programmer, the example that we talked about before, has a graduate degree or no graduate degree, in which case it's just a binary response, yes or no. So we could say 0 is no, and 1 is that you do have one. So here it is. We create a dummy variable or an indicator variable, 0 if the individual does not have a graduate degree, and 1 if they actually have a graduate degree. And then we run the regression again, and when we run the regression, we see that we still have a p-value of 0.0000, very strong. And in fact, if we now look at the coefficients for that problem, the constant is still not significant, but the experience coefficient is significant. The test score is significant because at a 5% level, and however the degree is not significant. 0.268 is the p-value. So in some cases, let me just mention that you may have some variables that are not, where the coefficients are not significant, but they actually help to improve the accuracy of your regression line. Interestingly enough, right? So it's a strange phenomenon, but it actually happens. If you actually remove those two things and you try to develop a prediction model, chances are your F statistic or your goodness of fit is actually reduced as a result of that. Okay. I already talked about more complex variables. Last but not least is the idea that we could have a curvilinear relationship. Let me just go here, back to here. So in a simple linear regression, we may have something like this. Y is equal to B0 plus B1x. If we want to have a curvilinear relationship, we could have B2 x squared, B3 x cubed, etc. All right. So in this case, but to be able to determine whether or not, you might find that a linear equation is not a very good fit, but perhaps a curvilinear equation is a much better fit. And so from the plot is what you would actually look at. If you have some values that go in like this, you say, well, I can't fit a linear line for it, but perhaps if I could fit a curve to it, it would actually be a better fit. So you would have to kind of explore that. And in the software, Excel allows you to try curvilinear relationships, whether or not you want to add a version of, like take x, for example, and then square it to order 2 or order 3. If you believe that it's a quadratic, say order 2, then what you can do is this variable x could be your x1, and then you could create x2. Sorry, x2, which would basically be your x squared. And now you go and fit do the multiple regression, where you have essentially you would have y is equal to beta 0 plus beta 1 x1 plus beta 2 x2, except that the values of x2 happen to be the squared values of x1. And you could try to fit the regression equation doing that way. So it's a nice little trick in terms of being able to do this, right? So you could see from this diagram right here, it seems like there's more of a curve. And so you could try to fit a quadratic to this, second order polynomial or quadratic. And then in Excel, you could actually do curve fitting, where you use a polynomial, and then you use order 2 to do that, and you get the following result. And you can see this is a better fit than what we had before, with an R squared of almost 90%. Sorry, I did not mean to include that. All right. So to do this in terms of linear regression, multiple linear regression, using Excel, that is, you would need to do what I just talked about a bit earlier, which is to square the first variable and then represent it as a new variable. You're creating a new variable, which is the square of the original set of values. Because if you just tell Excel, here's the data, y and x, fit for me a curvilinear model, it doesn't do it in terms of multiple regression. To use the multiple regression tool, you would need to create that second variable, which will take on values that is the square of the first variable. All right. So you can see here in this example, months versus months squared versus sales in this example. And then you have your multiple RR in terms of your output for this particular example. The correlation is pretty high, 90.9498. the R-square value, 90%, which is pretty good. And then you get the same regression table. And then you have the coefficients right here. And now you could see the coefficients of months squared is actually significant. The coefficient of months is significant. The coefficient of the intercept is significant if we use a 10% significance level. But if we use a 5% significance level, it is not significant. We will fail to reject the null hypothesis. All right? So I think that covers what we need to cover. Doing this in Excel is not very difficult. So I'm going to pause for a moment and show you how we do this in Excel.